All right, with this next section, we're going to be needing our data booklet. So if you can stop the video and go get your data booklet. And the reason I want you to get your data booklet is so that you can look at the equation that's on the screen that says B is equal to mu naught I over 2 pi r. And in your data booklet, it just says magnetic field strength, which is very nondescript. And it's really important that you understand that this equation only works when you've got a current, a single wire, and you're looking at the field strength, the magnetic field strength around that wire. Now, B, the capital B, is representing your magnetic field strength. And what I want you to notice is that it's inversely proportional to R. So, as you move further out away from a wire, you get a weaker and weaker magnetic field. So as R increases at the bottom here, B decreases. And I want you to notice that the field lines, the distance between the field lines, is increasing as you get further and further away. So you're going to, at this point, also learn your first hand rule. And these hand rules will be extremely helpful for you on the exam. So often it's the people know when you've reached a particular question because you start making all sorts of funny hand gestures during the exam. And people are using their hand rules. Now, it's important to know the right hand rule. The right hand rule is if you're imagining positive charge is moving through the wire. And of course, this is not the case, but whenever we're dealing with I, so you know when you write down the current I, so you're imagining that positive charge is moving. And you have to use your right hand, and the thumb is pointing in the direction of the current I. And what I want you to notice is that your fingers here are actually curved in the same direction as the magnetic field. So if we're looking at the fingers here, they're curved this way. And what way is the magnetic field? It's that way. And so your fingers are actually telling you the direction of the magnetic field around this wire. Now, if for some reason, and it likely will not happen, but it's a possibility, if they were to give you the direction of the electrons moving through the wire, you would actually use your left hand. Now imagine yourself, and your thumb is now going to be pointed down in the direction of the electrons, and you're still going to be gripping this wire. And what do you notice? If you're using your left hand for negative, you're going to see that you get the same direction of the field lines. So remember, conventional current I, hopefully you learned this last year, is in the opposite direction to electron flow through a wire. You use your right hand for I, your left hand for E. All right, now on to this equation. Oh, I should go over to this other diagram that I've got here. One of the ways that they identify the direction in which field lines are moving is by looking at the direction of compasses around a current conducting wire. And so you can see why this compass needle is pointing in this direction, and each of these is pointing in the direction of the magnetic field that's rotating around this current conducting wire. Okay, now on to our equation, which is B, which is the magnetic field, and the mu naught, that value is in your data booklet, so you might want to turn the page to your physical constants, and it's just below E naught, which you were using as your electrical constant. Now, if you remember, your electrical constant, E naught, was telling you how easily an electric field passed through the air. Well, mu naught is the same, but it's telling you how easily a magnetic field goes through the air or through a vacuum in space. And realize that this magnetic constant will change depending on the substance that the magnetic field is passing through. So you can only use this constant if you're going through outer space or air, and you can't use it for anything else. Also notice that in the data booklet, you don't have to calculate the 4 pi times 10 to the negative 7. You can use 1.26 times 10 to the negative 6 as your value that you sub into the equation. All right, so let's look, and then, and I, of course, is your electric current, which is going to be in amps as your units. And I'm certain everybody knows what that is. It's the radial distance from the wire to the point where you're trying to calculate your magnetic field. All right, so let's look at a problem here. The first problem says if a wire has a current of 2 amps, so we've got I, and running through it, what is the magnetic field strength 2.5 centimeters away from the wire? All right, so they've given us R, but we've got to convert that R into meters. So we'd have to divide by 100. And then now we've got to look at our mu naught value off of the data table and plug everything into this equation. So our magnetic field strength, and I'll go 1.26 times 10 to the negative 6 times the current, which is 2, divided by 2 pi, and then 0.025, and the 2's cancel, and I calculate my magnetic field. And unfortunately, I forgot to bring my calculator with me, so I'm going to have to stop the video, and we'll continue in a third video.